Okay, so we are now going to consider extensions of the limit concept. We have already seen what limits are. We have seen many ways of calculating limiting values of functions, and we have also seen many functions and in many cases where limits do not exist. We have also investigated the reasons for that. Now, there are two ways in which this notion can be extended. One of them is one-sided limits, and there is another one, infinite limits, which we will see afterwards, which in a sense actually is not a limit but simply a way of expressing a certain behavior of functions. So let us first see one-sided limits, and let us start our discussion from the formal definition of limits itself. We have seen what limits are formally using epsilon, delta, those things. So let's go back to that. When we say that the limit of a function f is the real number L at a, what do we mean by this? By this we mean for every positive real number epsilon, there exists a, again, positive real number delta depending on epsilon. It may or may not be epsilon itself, such that this implication is true. If we express this in word, it will be if the distance between x and a is less than delta, but of course from this we exclude the case x equal to a itself, because the function may not be defined at a but only around a, then the distance between f of x and L is less than epsilon. Now let us concentrate on the hypothesis of this implication. An implication is a statement which has two parts, right? The first part is what is given, and the second part is the conclusion. So that first part is the hypothesis. Now if we rewrite the hypothesis slightly differently, like this. You know that such inequalities are equivalent to some intervals. It's very easy to see, we have done this many times before, why these inequalities are the same as this x belonging to this set. So here you see a union of two intervals. One of them contains points lying to the left of a, and the other one contains points lying to the right of a, of course within the distance delta from a. So what the limit demands is that as x is close to a, okay, here we are looking at values x which are close to a, then f of x is close to L. But note that x being close to a at the same time can either be less than a, that is may lie to the left of a, or be greater than a, that is it may lie to the right of a. Now if instead of considering these two sets, we consider only one set, in only one of them, any one of them, say this one or say this one, then we get the notion of one-sided limits. Why? Say suppose instead of writing this implication, say there exists a delta such that I write this. Now I am not exactly writing down the same implication, because now my requirement is a little less. Okay, it is less severe. In the previous implication, I was requiring that for all values of x close to a but on either side of a, fx values should be close to L. But now I require that only for values of x close to a but on the left side of a. That much is enough for me now. But then of course I am not talking about the same notion. I am talking about a one-sided notion. So this is the notion of left hand limit, where we are using only the values of x that lie to the left of a. That's why I have chosen this interval. If this happens, if for every epsilon there is a delta such that this happens, which is a less stringent condition than this ordinary limit condition, then we say that fx has left hand limit L at a, and we use a notation like this, which looks much like the previous notation with one slight difference. To indicate that we are considering only values of x which are less than a, we put a minus sign over a, and that is as a superscript. Similarly, if one considers only the values of x that lie to the right of a, one gets the corresponding notion of a right hand limit. Okay, so that's how, tweaking this hypothesis part of this implication, we can have the new notions of one-sided limits. But all of these things look very theoretical. Now let's consider one example. In fact, the discussion in the text starts with this example, but I thought of showing it this way. Why not? Because we already know the epsilon delta definition. So it doesn't hurt to be a little theoretical in the beginning itself. And especially when it is something that we are already familiar with. Now the example that the authors have chosen to discuss this idea is one function which we have seen before. It is this. For any non-zero real number. At 0, of course, this loses meaning due to this denominator. Now let us draw the graph of this function. No need to be absolutely geometrically precise, we just need the notion. Now going back to what we did when we considered this function last time, you remember that when x is positive, then the function has the constant value 1. So to the right of 0, the graph is this horizontal line y equal to 1. But because it's to the right of 0 and not at 0 itself, so the line cannot touch the y-axis, and that's why we are putting this circle in order to prevent this line from touching the y-axis, in order to just show that. Similarly, when x is less than 0, then the value is constantly -1. So this time this is the graph. Okay. Now for a moment let us forget about that epsilon delta thing. What was our original informal notion of limits? Our original limit. The informal notion says that limit of f of x is L at a if f of x approaches L as x approaches a. But approaches a means it can either approach a from the right side or it can approach a from the left side. So in one-sided limits, the notion that we have discussed just now, we have made this one-sidedness by considering one of those two things. Okay. So if you only consider the x values that are to the right of a, you make x closer and closer to a, but always being on the right side of a. Then if f of x gets closer and closer to L, we say that L is the right hand limit of f at a. Similarly for the left one. So here also informally if you think like that, say your x is here and then you take it closer and closer to 0. X stays positive, so the value is constantly 1, and so the f values are constantly 1 means they are approaching 1 as well. So that is why for this function the right hand limit at 0 is 1. Similarly, if you are considering these x values and make them closer and closer to 0, then the values stay constantly -1. So the left hand limit of that same function at 0 is -1. You remember that when last time we considered this function, we proved that the limit does not exist. This does not exist. But now we can see that the two one-sided limits, however, exist and they have different values. In fact, it is this fact that they are different that this limit does not exist. So that is the notion of one-sided limits. Simply you bring the variable close to a from the right side. If the functional values get close to something, that is the right hand limit, and you bring your variable value from the left side of a. If in that case the functional values approach something, that is the left hand limit. They may not be the same and they may not exist also, because you see in our formal definition of this one-sided limits, because that's how we started, right? For every epsilon, if there is no such delta, if one epsilon is there for which no delta works, then the one-sided limit also may not exist, okay, will not exist. So that thing is there. Alright. You may be wondering about these figures because they take some time to draw, so I have pre-drawn them. We are going to use it when their time comes. That's why I am using only this part, this side. So we understand what one-sided limits are, but still let's see how the informal definition looks in words. So this is how the authors have done it. Informal definition, but when formally written, it looks like this. let a and b be real numbers where a is less than b. Let f from open interval a comma b to R be a function. We say that f has right hand limit L at a, at the real number a. Okay, I must mention that this L is also a real number. At a, if f of x approaches L, because this is supposed to be the informal definition of one-sided limits, that's why we are not going into those epsilon, delta, those things. Okay, we just simply informally write f of x approaches L as x approaches a in the interval a comma b. We have captured the one-sidedness by restricting x to b inside this interval, so that although x is approaching a, but every time we take one value from this interval, one value x, it lies to the right of a. Okay, so that's where the one-sidedness comes from. And we write a plus is equal to L. So that is the informal definition of right hand limit. To have the similar one for left hand limit, you just make small changes. You take C and A, where C is less than A, and instead of considering A comma B, you now consider C comma A, that this be a function. We say that f has left hand limit, the authors have written another letter, say M, at A if f of x approaches M as x approaches A in the interval C comma A. Now, opposite to what we have in the right hand case, any such x will be less than A. So this is the other side of A, the left hand side, and we write this. Okay, here we superscript, I mean we use the superscript minus. So these are the informal definitions of one-sided limits. And now comes one thing which we may overlook, or which we may not in fact consider at all while thinking about not one-sided limits but our original limit. Recalling the epsilon delta definition of original limits, we have seen that there are two sides, right? Two sides of A, and both of those sides are considered in the definition of a limit, original ordinary limit. So the condition is this, that f of x must approach L as x approaches A on either side of A, but lying in the background of this condition is the assumption that, see, the function itself, when we try to calculate the limit of f at A, the function itself may not be defined at A. This may not be there, f of A may not be there. However, there should be inputs available on either side of A. That is, you should be able to have points where you can calculate A to the left, lying on the left side of A, and also inputs lying on the right side of A. If the function is, say, not defined at all on the left side of A, then you cannot even ask whether limit exists of f at A, because there is nothing on the left side of A. So ordinary limit, you cannot even talk about that. You can only talk about one-sided limit, that to the right hand limit. And the next example means the first one actually makes that clear. You have to have inputs on both sides of A in order to talk about limits. The function that the authors consider is this. Consider the function f from this closed interval into R, and the rule for the function is this. It's a function, I mean, this formula defines a function which we have seen already in the part where we discussed functions themselves, and there we saw that this is in fact the largest subset of R on which this is meaningful. Outside of this it becomes meaningless, because you get negative number under radical, which is no longer a real number. It becomes a non-real complex number. So now you cannot go beyond -2 on this side and beyond 2 on that side. So that is why you cannot ask whether this exists. I mean, you can ask, of course, but it does not exist. That's because on the right side of 2 there is no input. So you can only talk about this one-sided limit, because only values of, only inputs which lie to the left of 2 are available. Similarly, you can also only talk about the right hand limit at -2, not the ordinary limit at -2. It does not exist. And if one calculates, of course, both of these values will be 0, which I am not again going to write explicitly. I mean, in the text you will see that the graph of this function has also been drawn. It is semicircular. Okay, the -2, you have 2 here. So at both -2 and 2, the relevant one-sided limits have value 0. Here the right hand limit is 0, and here the left hand limit is 0, but the ordinary limits do not exist at both the points simply because the function does not have those other values that should also be considered in order to calculate ordinary limit. Now, the relationship between the notion of ordinary limits and these one-sided limits should be clear by now. And it has been stated as a theorem. The theorem is simply this. There is a number also. Limit of f of x at a is c. What we write in place of c is not that, c is this one and L is this one. It does not matter, you can use any letter. If and only if, that is, the limit of f at c is L, and L of course is a real number, if and only if the right hand limit at c of f is L and the left hand limit also exists and is L. So if this is true, then both of these are true, and conversely. So that is the relationship between these limiting notions. And now let us come to example 2, which is about this graph itself. There is no need to try to write the function for this graph because we are only going to talk about limits at these points, the right hand limit, left hand limit. So we can see that from the figure itself. So let us see what the situations are at these points. Now, what is happening at the point x equal to 0? At x equal to 0, is it possible for but before we say anything though, you should understand that the function is only defined on this closed interval 0, 4. Outside of this interval, the function is not defined. Now, if you look at 0, is there any point discussing about this? No, we know that it does not exist because there is no input that is to the left of 0. This does not exist. We can only, and as a result, the left hand limit also there is no point discussing it because it's not there. What about the right hand limit? As x approaches 0, the functional values approach 1. So the right hand limit does exist and it is 1. What happens at x equal to 1? Here, the left hand limit, that is, as x approaches 1 from the left side, the functional values approach 0. So the left hand, let me write it briefly like this. The left hand limit L is at 1 is 0. And what about the right hand limit? As x approaches 1 from the right side, the functional values are constantly 1. but there is one more thing also. The functional value at 1 is also equal to 1. You see this black circle, at this point this is not the value, this is the value. What happens at x equal to 2? At x equal to 2, both the left hand limit and the right hand limit are equal to 1 because of this nature of the graph. However, the functional value at 2 is 2. So here at 0, one of the limits does not exist, one of the one-sided limits, namely the left hand one, and as a result the ordinary limit also does not exist. At 1, both the one-sided limits exist, but they are different. So by theorem 5, the ordinary limit in this case also does not exist. However, the right hand limit is equal to the value of the function at that point. At 2, both the limits exist and are equal. So the ordinary limit also exists and is 1. However, that is not equal to the functional value. So you can now guess what will happen at 3. At 3, both the left and right limits exist and are equal to 2, and in this case that is also equal to the functional value. At 4, we have reached another boundary point. So here we can only talk about the left hand limit, not the right hand limit, and as a result the ordinary limit also does not exist. The left hand limit is what? 1, but that is not equal to the functional value, which happens to be 1/2. Okay, so this pretty much sums up the notion of left and right limits. So you see that in spite of having different left and right limits and having them different from the functional value also, and as a result ordinary limit not existing in at many of these points, but in all of these cases the one-sided limits that we considered themselves existed, right? But that is not necessary. That may also not be the case every time, as you can guess, and this is where this next example comes. So in example 3, we are looking at a function which has very wild behavior near 0, and the function is this. Sine 1/x, where x of course is non-zero. Its graph looks like this. The graph is there on both sides of the y-axis, that is for negative x values, positive x values, for both values. And being the graph of a sine function after all, the graph has that wavy nature. However, as you go nearer and nearer to 0, okay, as you get closer and closer to 0, the oscillation increases in frequency. As you get far away from 0, the oscillation is much slower, but then it increases in frequency. So that's why there is this effect that you can see. The graph is getting compressed near 0, which means that as you get okay, just for the sake of clarity, let's forget about this side. Let's concentrate on the positive side. As you take your x closer and closer to 0, of course, the sine 1/x values oscillate between 1 and -1. That is there. but the oscillation increases in frequency, and it of course continues to go like this. It oscillates more and more rapidly, so that although the functional values stay bounded, they do not go above 1 or below -1, but they fail to settle at a single point, which makes both of these one-sided limits not exist. This does not exist. The right hand limit at 0 does not exist simply because f of x never gets close and stays close to some L. It is always oscillating between 1 and -1, and the closer you get to 0, you see there is one point that should be understood here. Say this is your C, small c. Now if you want to see what is happening, what is this function doing at C, you just draw a perpendicular to the x-axis which goes through C. That perpendicular intersects the graph here. So the function has the value this at that point, and near C, whether you are to the right of C or to the left of C, the functional values actually get close to that point, okay, and they settle at that point as the limit. So this exists, and is f of c, which is just sine 1 over c. But because of this ever increasing oscillation near 0, this does not happen. It's a little difficult to understand, but I hope you can understand. At any positive real number, the limit exists, but at 0 it does not exist, even when you come from one side. A similar problem will occur on the other side also. So that is why at 0 the limit fails to exist. Both the one-sided limits do not exist. And this non-existent behavior of one-sided limits, this is exhibited by unbounded functions also. In fact, if one reduces the complexity, so this is example 3, no? If one considers instead this, simply f of x equal to 1 over x, so x is not equal to 0. If you consider this function, here you do not have sign, and if you draw the graph, you know its graph also. On the positive side it will be like this roughly, and on the negative side it's like this. So as your x approaches 0, the functional values get bigger and bigger. So here also they do not settle near a point as x approaches 0. But the reason here is that the functional values get bigger and bigger. So they never settle at a single point. And here also they get, from that side also the functional values get bigger and bigger in size, but with a minus sign. So there also they do not settle at any point near 0. So here the reason for the one-sided limits not existing is too much oscillation. Here, unboundedness. But here also, in this case also, both the left and the right limits at 0 do not exist. In this case also, at 1, the at 0, the left hand limit does not exist, but for an entirely different reason. That's because we cannot even consider it. In these cases, we can consider them, but they do not exist. Now in example 4, this has been modified a little bit, but before that there is example 4 is about the second extension of the limit concept, infinite limits. In fact, this example that we have discussed just now illustrates this point. You see, when x is approaching 0, the functional values are actually increasing without any bound. However, sometimes we say things like this, right? Infinity. Infinity should not be thought of as a real number because it's not. Okay, it's not a real number. When we see something like this, it just simply means what I have said just now, that as x approaches 0 from the right side, the functional values increase without any bound, and given any real number, however large, those values eventually exceed that real number. Similarly, this, as x approaches 0 from the left side, again the functional values increase in size but with a minus sign. So they eventually exceed, means I should not say exceed, but they become smaller than any negative real number, any given negative real number. So these are the notions of infinite limits. It's an extension, and it's in fact just a language of saying something. You see, the ordinary limit or one-sided limits actually are not existing in these cases. We have said that just now, right? But there is a certain behavior shown by the functional values which we are trying to capture in this language. That is, if it is like this, then we say that the right hand limit is infinity. Right hand limit is infinity means that's not ordinary limit, but it's infinite limit. Similarly, here the left hand limit is minus infinity. So that's the notion of infinite limits. It will be made precise, we are coming to that, but let's see example 4, which is just a modified version of this example. In this example, it's a sort of a question itself. Find this one-sided limit, and this one-sided limit. It's just a modified version of the previous example because here only a shift is involved, nothing else. Other than that shift, this example is essentially just this one. You see, if you try to draw the graph of the function that is involved here, it will look like this. So here the point that at which we are considering this one-sided limits is 1. And the graph looks like this. So it's just this graph shifted by 1 unit to that side. And you can clearly see that in this case also, this one is infinity and this one is minus infinity. It just becomes clear from this figure. So if you want in the text it's given as a geometric solution, but let's look at the graph, which is just a shift of this graph. So from the previous example we have these limits. Or you can consider an analytic way of solving this also, in which you just simply say that as x approaches 1 from the right side, x is greater than 1, so that x minus 1 is positive, but as x is approaching 1, x minus 1 is approaching 0, but at the same time it is always positive. So that's why this one-sided limit is plus infinity, and similarly that other one-sided limit is minus infinity. Let me just refill it a little bit, running out of ink. So you should be able to understand by now what the informal definitions of these notions are. That is, when you say that, say, we were considering A, right? So let us consider A. What is the meaning of this? The meaning of this is that as x gets closer and closer to A, as x approaches A but from the left side of A, the f of x values, the functional values, increase without any bound. That is, given any positive real number, they eventually exceed that real number as you take x closer and closer to A from the left side. Similarly, you can have this also. As you take x closer and closer to A from the left side, the fx values go below any given negative real number. And you can understand that you will have similar versions for the right hand limits. And correspondingly, there is also a statement that can be considered like this. That is, as here it's not one-sided, okay, it's two-sided. As x approaches a, either from the left side of a or from the right side of a, the functional values, it does not matter, the side does not matter, the functional values, all of them increase without bound. Similarly, if you have a minus sign here, they all go down without any bound. These notions are very natural, so you can understand. Any one of them is given what its meaning is. Now, let's see the next example which has two such functions. Example 5. So, example 4 had one-sided infinite limits. Oh, perhaps we should not say that the limit of this is this. Perhaps this is how we should say that the infinite limit of this is this. So, the ordinary limit, the distinction between ordinary limits and infinite limits can be given like this. If our limits are infinite, we explicitly say infinite limits. But now we are going to see two-sided infinite limits. Discuss the behaviors of the following functions near which point it will be given there. So the first function is this 1 over x square near 0, and the second function is 1 over x plus 3 whole square near x equal to minus 3, that is minus 3. So if one similarly in this case also draws the graphs, say we draw the graph of the function in part A first. Because of the presence of square, here no output will be negative. In fact, you actually cannot have zero output also due to the nature of the function. Now the graph looks like this. It has two parts. There also for 1 over x and 1 over x minus 1 also there are two parts, but in this case those two parts look like this. Because we have squares, so for negative x values also the graph lies above the x-axis. So here you can see that as x approaches 0, either from the right side or the left side, the functional values increase without any bound. So that is why you can say that the infinite limit of f at 0, it's a two-sided infinite limit, is infinity for this one. And just like that case is a shift of the graph that you saw before that, this one is also a shift of this graph. Let me show it there. So this is x equal to -3, and the graph of this function is just this. So for this one also, the two-sided infinite limit at -3 is infinity. Next, example 6. In example 6, there are many parts where behaviors of rational functions will be investigated at points where their denominators become 0. I mean, some limits are going to be considered. In part A, we have this limit of x minus 2 whole squared divided by x square minus 4 as x approaches 2. Now here, of course, the ordinary limit itself exists. It's a two-sided limit. Okay, you can see that there is no plus or minus sign. So after cancellation of that x minus 2, you see that the limit is nothing but 0. In part B, the function is x minus 2 over x square minus 4. So here, that similar cancellation gives us 1 over 4. Because the problematic factor x minus 2, you have been able to cancel it from the function in both these cases, that we are having ordinary limits. Ordinary limits are existing in these cases. But next comes this. This is a one-sided one, 2 plus x minus 3 over x square minus 4, and there is a high chance of making a mistake here. Two plus. Now if one factorizes the denominator, one of course gets x plus 2 times x minus 2. However, okay, now there is no way of getting rid of x minus 2. So an infinite limit will appear. But which one? Plus infinity or minus infinity? We have to carefully see the situation, okay? So the point at which we are considering our limit is 2. And near 2 we also have 3, right? Note that our x values are approaching 2 from the right side. So the x values may originally be somewhat far away, okay? But because they are approaching, eventually they will have to come between 2 and 3 like this. For such values only, after all, we are going to consider the ratio and see where the ratio values are approaching. So say you have some x value here. For that x value, x plus 2 of course is positive, right? What about x minus 2? X minus 2 is also positive. Why? Because 2 is less than x. But what is x minus 3? For this x minus 3 is negative. And this continues to be the case no matter how close x is to 2, if it lies between 2 and 3. So that is why, although we know that the values are increasing without any bound due to the presence of this x minus 2 in the denominator, but at the same time any such functional value is coming with a minus sign. So that is why here the infinite limit is minus infinity, and the authors have also written as x, what is that exact? Now I don't think I have written it here though. As, let me write the function itself, is negative near x equal to 2 as x approaches 2 from the right side. Okay, so that's why here the infinite limit is minus infinity. The next one is going to be just its opposite, because in this one we are going to consider the left hand limit but of the same function, that is x minus 3 divided by x squared minus 4. So if one argues similarly, in this case the infinite limit will exist and it will be plus infinity. I am leaving the little argument that we had here in this case to you. E. Do you see how strange it looks? Here we do not have any prejudice in calling these things limit, minus infinity and infinity. Here, however, we are saying that the limit does not exist. But that is because even in the infinite case, we will say that such a two-sided limit exists if there is a consistent behavior shown by the functional values. Because to the right of 2, the functional values are going down, whereas to the left of 2, they are going up without any bound. So there are two kinds of behaviors on the two sides. So that is why there is no consistent overall behavior near 2 if we consider both the sides. So that is why even the infinite limit in that sense also, this does not exist. It will become much more clear when we formally define infinite limits. Okay, we are coming to that. And finally there is another one, part F. Two minus x over x minus 2 cube. So there is a cancellation. This one is also two-sided. Yeah. Now because we have x minus 2 whole square here, so that whether you are considering x to the left of 2 or to the right of 2, this one has an overall consistent behavior. Without the minus sign, it's approaching infinity, but with the minus sign, it's approaching minus infinity. So that is why here there is an infinite limit which is minus infinity. The actual formal definitions of right hand limits and left hand limits, although we have seen that, but the authors have presented those definitions slightly differently. We have seen the informal version, right? But let's see the epsilon delta version. We say that f of x has right hand limit L, which is a real number at for some reason here the authors are considering the point x naught, where we are considering the limit. If for every positive real number epsilon there exists a positive real number delta such that, now you know what to write. It's an implication, but we are going to write it like this. And similarly, there is one for the left hand limit, in which case you have to consider, in place of these inequalities, x naught minus delta less than x naught implies this. Okay, you understand that. So that is the formal definition of one-sided limits, and you can understand that these inequalities are equivalent to this condition. So in this form, in fact, we have seen the formal definition already. So same thing. But now let's finally come to the formal definition of infinite limits. Not one-sided infinite limits, but two-sided infinite limits. One-sided infinite limits also can be similarly formally defined. That is left to the reader. I mean, it's like that in the text. So I will also leave that to you. Instead, let us see formal definitions of infinite limits. Limits means two-sided limits. And the definition of course goes like this. We say limit of f of x as x approaches x naught is infinity if the functional values increase without any bound, which means what? Now we are not trying to make f close to L, but in a sense close to infinity. So we want to be able to make the f values as large as we want. How large? Namely, if we are given any positive real number, we should be able to make the f values even larger than that. So that's how this definition comes. If for every real number b greater than 0, this b is, you should think of it as a big number, okay? Although there is a formal definition has nothing like big or small, these are vague terms, but thinking of these things in your mind, you should think of b as something very big. Can you make the f values even bigger? Yes, if you can, then this is the situation. There exists a delta greater than 0 such that implies, but this time f of x is greater than b. Similarly, if you have minus infinity here, then this part will be same, but here you will write f of x less than minus b. That is, you can make the f values as negative as anyone wants by choosing, you can make the f of x values as negative as you want by choosing x sufficiently close to x naught. Note that here we are considering both the sides of x naught. That is why you have two-sided infinite limits or two-sided ordinary infinite limits. But if you want one-sided versions of this, besides this, you will have to change the hypothesis also. You know how, okay, by considering only one side of x naught. So that's where the section ends. After this, we have the exercises which we will solve in the next calculus update. And our next upload is this coming Friday, of course. What shall we do? On Friday, let's go back to field extensions again. So that's just it for tonight. See you on Friday. Until then, this is me, Lucifer, signing off from a mathematical room. Have a nice night.